lecture and for the new friend joining today. So today's is the final lecture, and the overview of today's schedule is first we will talk about the main theorem. So the main theorem is we show an open dense subcollection of hypersurfaces under some assumption which will be clear. Defined, but it's a very general collection of hypersurfaces, and we show that open dense subset of them are static regular, and together with our existence and local uniqueness result earlier, that tells you for if you have a background static vacuum matrix with the induced Bartnik boundary data, and you do small perturbation, and those perturbed boundary data will have static vacuum extension. So then the theorem will be relatively shorter than the convex case we presented yesterday, as I will do the setup, and then I will talk about an assumption we call a star, and we will show that in fact the assumption holds where the open dense set open dense condition comes in, because this assumption holds for open dense set of T. And then we'll give a proof of main theorem on the assumption star. And so that can stop there if the background is Euclidean. But then in the background, that's in our second paper, if the background is a general static vacuum matrix like a Schwarzschild, and then we need to use an additional ingredient, that's a classical work of Nomizu for the local extension, global extension of local Killing vector field. But then here we're working on so-called H Killing vector field. And then I will end the sequence of the course by how it really related to Bartnik's quasi-local mass, not particular conjecture. And then there's of course, a lot of open questions, but at least something I think is more relevant to extension results we have been talking about. Okay, so the setup. So we are looking at a background asymptotically flat static vacuum matrix, and we'll assume U bar is positive. And U bar is positive is needed, is really in the existence and local uniqueness result. When we set up an elliptic boundary value problem, this appear in the elliptic coefficient, so we want to be positive. So here is defined what kind of family of hypersurfaces we can make that happen. So first, sigma t in our case will always be the boundary. So the picture will be, you have boundary of region. So this can be the boundary of the ambient manifold. And then this is the region omega t, and this is the boundary. And we also require the boundary to be sigma t to be embedded in the big space. Okay, so we say this family of hypersurfaces is we're showing smooth family is one-sided. One-sided family of hypersurfaces. Foliated along a subset with relatively, there's some fundamental group assumption. It's relatively simply connected sigma t hat in the exterior. So I'm going to draw a picture to illustrate it. If this following condition holds, so, and actually we'll need here, probably let me assume, we need to assume this subset to be analytic hypersurface. It's a technical assumption. Right now we are not able to get rid of in the general case. So if this portion of sigma t hat So let me draw a picture of a readable size. So this is a family. We have sigma 0, sigma 1, sigma 2 continuous in T. And so we can fix this to be sigma. And then this is the portion that is foliated. So this is a portion that's sigma T hat. So sigma T can coincide with sigma on other places, but there's some region it has to foliate it. And then we require this portion to be an analytic hypersurface. Each of the sigma T hat is analytic. This condition can be dropped if the background is Euclidean. And then we require being one-sided means you have a deformation vector. This is the deformation vector. It's a vector field defined in the neighborhood of the surfaces. And we require the normal projection is always greater or equal to 0. So that means one-sided. We call this zeta. Zeta is greater or equal to 0 everywhere, but in particular, along this foliated path, zeta is strictly positive. So this is zeta here. That's the normal projection, and this is positive sigma T hat. And then the relative simply connected assumption is the one probably a bit strange. And the thing we required is the pi1 fundamental group of exterior region relative to this piece is 0. Right? And geometrically, it means any two curves which reach this boundary portion, it doesn't have to exactly endpoint, but another curve from starting point here in the ambient. These two paths are homotopic to each other. So you allow this to move along sigma T hat. So while this looks quite complicated, but the reason is we want to push to see what our argument can extend, right? So for example, foliation will be much easier. For the foliation, then you have, you can just choose sigma T hat to be sigma T everywhere, right? So if a foliation, in particular, the foliation in Rn will also, we can also drop this relative fundamental group assumption. So it's only, we only care about the ambient. There is some really topology outside this part in the exterior region. That's what we worry about. But again, we don't have any example of static vacuumetry, which can have some weird topology outside, but that's what in great assumption we need to prove for this generality we want. So example would be like foliation, any foliation. Of boundary in R and will satisfy all those assumptions. But it doesn't have to be foliation, even R and right, you can have just foliated one part of it. Okay, and the theorem is now so the theorem is there, so give me such a foliation, give me such a family of surfaces, then there is a open dense J in where T is defined. Let's say T is defined between some number, like say delta minus delta, can be very, very large. We don't really care it has to be small or not. But then give me any family of some parameter space for T, then we say there's an open dense set J in this parameter space such that sigma T is static regular. For T inside this open dense set J. So that means if you have this family, and then so there'll be only like a very, very few of them which does not static regular. All rest, the open dense set will be static regular. Once it's static regular, and then we can apply our existence, so then we can solve the prescribed boundary value problem there. Okay. Question so far? Let me see if there's any question for the statement. All right. So let's look at the setup.
Question. So the property of being static regular itself, is that an open condition?
It's not clear, right? It's not clear. It's with open condition. But I think essentially in this, that would be followed from this proof.
Oh, but also, I guess there's another separate question, which is that static regularity implies a certain kernel fact, which implies the solvability of the problem. So is the latter thing open condition? The ability to solve the prescribed problem locally, right? Is that an open condition?
No, I think it's not clear, right? As that's what the main purpose, like for example, while we have your fixed static vacuum background, we already have one boundary that is solvable, and then we show that nearby one will be solvable. So essentially,
sorry, the property of the property that nearby ones are solvable, that property,
right?
Is that open? Right, just that the kernel is trivial.
Right. So I think you should think about that's our existence local uniqueness result. Once we say static regular and we show that condition is open, because nearby one can be also have a static vacuum extension. But now also with static regular is an open condition, and that's essentially proven in this theorem. So it doesn't follow trivially from just the setup whether it's open, but it requires all these efforts to show that. So in other words, our theorem can be interpreted in the sense like some condition is open and some results, some existence result is open. It's an open property. Yeah. All right. So here let me just for the illustration purpose, just do like foliation. And this is really purely really analytic condition. If you remember what a static regular means is you have a kernel element, then the kernel element will satisfy additional boundary condition. But now our domains are changing. We have omega t and the boundary sigma t there. How about let's think about this? We fix 0 to be the one we're going to fix. And then we have omega t, which is for the illustration purpose, is the larger region here is sigma t. And this means we were looking at this operator, which is defined for each exterior region with the boundary. That's the linearized operator. Let me just say this is the static vacuum operator, the linearized one, and it's linearized at the flat matrix. For the region where it defines change, so it's in m minus omega t. And then we have the boundary condition. And it's also defined on a changing boundary, right? So I think, so here, presumably I should denote t because the operator, the formula of operator is the same, but the region is changed, right? So it's really different problem. It works on different function space. And the common thing is we use pullback to fix the domain. So since we have the foliation, the family coming from this deformation vector. So it generates a diffeomorphism of the ambient space, the exterior space. So we can pull back the sigma t back to the fixed one. We say, for example, you can choose any t to fix, but in particular, let's choose the one t equal to 0. And this is sigma 0, we call that sigma. So we have a diffeomorphism defined in exterior, we can pull back everything on the fixed region. So now we get, will be a family of operators defined for the same domain function space, but operators will be different. So that's we call the family of corresponding operators. Okay, so we call this GT and UT. It's really the fixed background static. Is it working? It's really the fixed background, but the region is defined on different region and pull back to the same in an exterior of omega. And then this pullback operator we denote by LT, and it will be just you. All the everything, the coefficient operator, differential operator has to pull back. Well, it just be the static vacuum operator linearized at the pullback. Okay, and then we have the boundary data. So now, if I think about as operator, apply on this pair H and V. So this is really just symbolic notation. It denotes the operator which you pull back here. And so this is going to be, if the family is smooth, it's going to be a smooth family of operators now defined on the same function space. All right, so again, we denote the operator L0. L0 is the one we fixed, right? So at L0, this is LT equal to 0. This is just the setting we've been using, the fixed background static pair without any diffeomorphism involved. So this we denote by L. Okay, so in order to prove that theorem, it turns out we just need to prove this theorem prime. So theorem prime says we want to say sigma 0 is static regular. So that means we look at the kernel element of t equal to 0, so L. So suppose right, and we want to show the conclusion will be then so this will be the conclusion. So we want to show if it's kernel element, we want to show particular at t equal to 0 is static regular. But of course, we don't expect that, right? So this theorem tells you we cannot really say which t will be static regular. Suppose, but here is the missing assumption. Star. So what needs to happen at this particular time t equal to 0 is let me box this assumption because I go across the other side. So this assumption need to happen at that time equal to 0 in order to conclude the stronger boundary condition holds. That condition say this is the kernel element at t equal to 0, and it has to be approximated by kernel element from other time. Moreover, that family approximated at h and v need to be differentiable in this sense. So the derivative exists. And
So
PZ could be anything. It just exists, right? We denote by PZ. And the upshot is how theorem prime implies theorem is we prove this condition holds probably not exactly at t equal to 0, but we holds at an open dense set of the space T. So this is a remark. So first, before I say what exactly we prove, this condition in general, you will find out is, of course, will not be true for every t, right? So the simplest example will just be even if you have elliptic operator, even without imposing boundary condition. So this is a hold for general PDE. So if you just take this family of operator to be, in particular, the Laplace or Helmholtz operator, right? Just the one with number t. So if you have a function and then you apply this, and where it has non-trivial kernel elements is exactly the eigenfunction. You can even look on the closed sphere, for example. Right? So if U is a kernel element, means it's eigenfunction. But then the eigenvalue is so far apart, right? If you have eigenfunction, then the eigenfunction cannot be approximated by kernel elements of a nearby t because the nearby t is trivial kernel. So this condition will definitely does not hold even for a nice elliptic operator. But from this, we actually see where it fell. It can only fail at some really discrete set, right? Like a very few of t, it will fail that property. So what we show is, we show essentially this holds right? But not exactly this one. Neither we show a discrete version. Discrete version means we only have a sequence converge, not this in T. But then we also work out there's a difference quotient, replace the derivative. So it can be worked out. And this is just follow from, so we formulate using our static harmonic gauge. So we show this essentially, you can rewrite, consider the elliptic problem, and we use the property, which also proof in the paper, is the nullity of an elliptic operator. Nullity is the dimension of the kernel space. It's upper semi-continuous. So upper semi-continuous, really like this picture. The nullity can only go up, right? But then where it has jump is only the complement of an open dense set. Okay, all right. Let me pause if you have any question. So the rest of things to prove this theorem prime. Okay. how about, let me erase. Let's see, I think probably I want to keep these operators, and let me erase the remark. Okay, so now we are in the situation, we have a given H and V, which is kernel, and we know it will be approximate by a nearby kernel elements, and with this property. Okay, and so this in the kernel, just using this notation in the kernel of LT, that means right? You agree? That's exactly just what definition be in the kernel. So this term is 0 with some boundary condition we'll also use very soon. So we want to use this to construct another element which such as this is 0, because we want to apply our green type identity as like a test pair. So what this have, this is sigma, and we have HT defined because the pullback didn't also fix the region. So HT and VT defined here. So they are linearized. So they are a solution to this linearized equation, the linearized static vacuum equation. But then we also have, of course, the one H and V, which is defined also everywhere here. It's also equal to 0. But the thing is, the operator is different with respect to different matrix. This is a pullback matrix. So in order to make it happen at the same matrix, so we looking at the restriction. So this is omega t, a larger one. But we look at the restriction of H and V. It's too light to see. In the complex exterior. So this is a solution to the static vacuum equation outside this region, right? So it's going to be a solution when you pull back everything inside. This both happens and okay. And now if you differentiate in T, so ideally if you differentiate in T, so if you want to construct other solution, if you differentiate T, then if you ignore this term, if this is fixed, then you have a differentiation, you have H prime, V prime. That should be a solution, right? But unfortunately, where this the linearized matrix also changing, in other words, the coefficient also changing. So you also linearize operator, so you get the second partial derivative, and then you get G prime, comma the evaluation of this. And that's the term we want to cancel out. So then we construct this, and we differentiate in T both, and subtract then. And using this pair and that pair, when you evaluate at T equal to 0, they are actually the same. So that's this property. So when you differentiate in T, subtract these two, what's left is only the linearized operator. The second order partial derivative exactly canceled out. Get this G bar and H prime, V prime 0 minus the derivative, this, it becomes Lie derivative. So Lie derivative because we have a vector field X. So by doing this, we do construct a new static vacuum deformation. And this is using our notation, that's PZ minus HV is given, right? But this is a Lie derivative on this pair H and V. This is Z minus, and which we call KW. So that would be our test pair for the green type identity. But then we still need to know the boundary condition. So let me write down, and if we have time, we'll show you how to derive the boundary condition. Using all those properties, this actually coming from the kernel, so we know what the Bartnik boundary data would be, right? And this, we can also compute the Bartnik boundary data, very similar to the computation we did for the convex case yesterday. So the upshot is the static vacuum pair. We know what exactly the Bartnik boundary data will be. So here we assume H satisfies the geodesic gauge. Then this, if we define KW, just let me recopy what I wrote there. So this is PZ, the one from this assumption, minus the derivative of the given pair. Satisfy zeta is the the lapse of this family of services, right? So we'll assume zeta will be greater or equal to 0 and is positive when it's foliated. So now we apply the green type identity. So the green type identity for any pair of H and V and KW, we are going to choose exactly the notation really fits our current setting. Is the HV is the one we given in the kernel of T equal to 0. K and W is the one we construct. And then there will be the green type identity tells you there is an interior integral equals to the boundary integral. But then for our setup, interior boundary integral will be 0. So only the boundary integral left. So that'll be Q of H and V inner product with the Bartnik boundary data of another pair. And there's another boundary term, so it's more like a little bit like self-adjoint, right? So that's Q of K and W inner product with the Bartnik boundary data of H and V. But our setup tells you this has 0 Bartnik boundary data, so that term is gone. Now we just, what's the formula here? So the upshot is once you write down the formula, and this will tell you this equal to the DAH square, which we want to show to be 0. Right, so the green type identity, let me continue this equality here. So it's VA. That's the whole term Q. And then for the Bartnik boundary data of this is the dot product of minus. All right. So let's do a computation together. So we have this term will be multiply this, so we minus 2V A dot DAH, right? But it's minus, so it's going to cancel out this. It's a plus of the same term. So the other next term will give you minus 2 zeta and dAh squared, which is the variable term. And then this term will give you some function. So it's a normal derivative of v, and then g here. So there will be a trace of this, but the trace of this will be dh of, so the linearized mean curvature of h, which is 0 by assumption. So then you trace back, you see it's 0. That tells you this whole term is 0. So now we separate two cases. So for those of you who join, everything I talk about is a joint work with Zhongshan An. And this result is actually a combination of the result of our two papers. In the case of foliation, is in our first paper, and in the foliation in Euclidean case. So in the case of foliation, sigma t is a foliation, then we know zeta is positive everywhere. So then we can just conclude. Right, so this conclude the AH is 0. Sigma, and then we are done. Because now that's what we aiming to prove. And in the case of not foliation, we have to do a little bit extra in gradients. So for the general thing, the one-sided family as we defined earlier, we only know because zeta could be 0. It's 0, it's positive only when we is foliated. Right? So then we cannot really say anything about this away from this subset sigma hat. But then we get the A, which is 0 there. But observation is, if we go back to this extra pair we construct, it always comes with zeta multiplied dAh. So if zeta is not 0, dAh is 0. We don't know the information of dAh, but zeta is 0. So we observe Kw, the one we construct, we know it's static vacuum inside, but we didn't really know what the boundary condition is unless we compute. It turns out it's also it's a new kernel element. But then did we just prove any kernel element must satisfy this condition? dH will be 0 there. Now we can replace H by K. So there's an inductive argument involved. So we can show the A, K is 0 also on that part. And it turns out the AK will be, see, squeeze in here. So it turns out that's the normal derivative. So we can covariant of dAh. So that can recover back to extra information for the original kernel element. And we do that inductively. It's more or less straightforward computation. Yes, right. So how about let me finish this and we can see the computation. Right. This, right. I think it's like the notation becomes overwhelmed now. So I will recall what properties we get for this P and Z, and then we can show the computation. Okay, so right, it turns out zeta never Z never come here, right? You mean zeta or Z?
The zeta.
Oh, zeta. Right, the zeta comes from X. That's the normal part of X. And the tangential part will always be 0 by our assumption. So we really need to compute the normal part, which the zeta comes from the normal projection of X. So if we do that inductively, then we get this for any normal derivative of this quantity is 0 on that piece of hypersurface. Okay. And then it turns out if you working with geodesic gauge, we work with H in the geodesic gauge, then it tells you H vanish at infinite order. So this is for all order of derivative, and tells you this for all order derivative also vanish sigma hat. So that's where the analyticity comes in. So we have H which vanish of infinite order. So we can choose H to be, so it's a bit tricky there. So first we choose H in the static harmonic gauge. So by ellipticity, we know H is analytic, but then we can impose the analytic geodesic gauge that's been proved in our recent, so our preprints to be posted. So together with analytic geodesic gauge, then we know if it's analytic quantity and the surface is analytic, so and it vanishes at infinite order, it has to be 0. It has to be the 0. So H is locally trivial. So one thing we also use is a classical result of Muller-Hagen. The analytic matrix is static vacuum matrix, and the potential are analytic. So we have to work out with some coordinates with analytic. Right, and then we actually, that's a very good point. So we have, once we give a family, we know there's a fixed J, which will not depend on which we choose. So you fix J, and that's really the operator property. And that's from the nullity of semi-continuous. So we know there's a fixed J such that if you work on the T inside the J, it has this property. Every kernel element can be approximated by a nearby one. It's a very good point, and but it can be, it's done. Right, potentially worry like this will not approximate, although it lies on the same, it's a kernel element of the same operator. But our statement says for that particular operator, any kernel element will be approximated by nearby one. So then this shows it's local, right? And where those, so I will get back to this computation very soon.
I think I understand that. So you don't need to explain it because you're going to learn it.
Okay, probably later because I want to see how you close up the argument. Probably will do that after the lecture. Then, so we show its neighborhood, but then how do we extend to show H is actually trivial in the sense it's coming from the lead derivative of vector field? So it has to be trivial. We use this theorem. So this there is extension. So probably let me give you a name. So if we fix a tensor, 0, 2 tensor, symmetric tensor H, a vector field X, we call that H killing. Right, so you should fix probably given background manifold. And so that's exactly the one. Just give a name for this operator of this quantity we use frequently. So this is called, the vector field is called H killing. And the theorem is about the extension of local killing to global one. Right, in the case where H is identically 0, that's just a classical result of Nomizu in 60s. He said under some condition of like a kind of strong condition, analytic manifolds, and then your local Killing vector field has a global extension. And we extend that result to this more general vector. And let me state the result here. As I said, it's when H is 0, let's just prove an Nomizu. And we learned this result in the work of Anderson. So he sketched a proof. We gave a different proof based on extending Nomizu's original proof. Okay, so let me draw the picture of what that. So that's exactly the pi1 condition comes in. We need. So this says if you have a manifold, just say that's the whole blackboard, and then we have a region U, and here we already know X is a H killing. H is defined everywhere. H is analytic, and you know locally this is coming from a vector field. Then you can extend the vector field X, such as find a global vector field coincide with X here, and outside is also H killing. And where the these conditions come in is the extension in either Nomizu's original proof or in Anderson's sketch, the argument he outlined is by working out the extension along a path. Right? So given a point here and you solve something, you extend the vector field along it. And the problem you worry is if you have anything defined, you start do the same process, another point of U where the vector is defined, and you get this point, the vector field, whether it will match or not. And under this condition, also any of these two paths are non-homotopic, so you can connect by family of homotopic paths. And you know for each closed one, the extension will be the same. Then you just do that step by step. So you know any two paths, you do the extension, you get exactly the same extended vector field there. So the vector field is well defined. And this condition is necessary for this theorem because their counterexample is already in Nomizu's work when H is 0. And the counterexample is, for example, like a torus. If you choose, torus has non-trivial fundamental group, but if you choose the open small disk in the torus where you have a rotation vector field, a flat torus, and then you can extend the rotational vector field a little bigger, but then when you match, it actually doesn't, globally it does not give you a global vector field because it depends on where you extend the vector field across the non-trivial topology. Okay, so I think that's a good time. We'll take a break. How about let me just say how we finish it, right? So now we already have local one, and then we have the assumption. This is relative trivial fundamental group. So a neighborhood is also have that property. So we can apply the extension to show H is in fact trivial globally, and then that finish the argument. Okay. Right. So should we take like a 5 minutes break? And so you finish everything I wanted to present, and I feel like in this direction, not only this direction, but recently in mathematical relativity has been tremendous progress. I think really because we have very many talented young mathematicians join this field, like my collaborator Zhongshan and many here and also online. And I'm really happy to see that. So I feel like I'm not really at the stage of really talk about open question yet, but I still try. So at least I review some of the existing open questions, which I hope will motivate some of you to work on this direction. So this conjecture of Bartnik originally is really coming from his quasi-local mass, which I have not really ever mentioned. So I want to talk about the relation to quasi-local mass here. So there are, of course, many beautiful definitions of quasi-local mass by Huang, Yao, by angular momentum work of Ponin, and so there are many tremendous progress. But Bartnik proposed this differently. So I always feel like a Bartnik's conjecture is more like a strong positive mass theorem in some sense. It's really you want to understand positive mass theorem in the case with boundary, right? But not arbitrary boundary, but really with some boundary data, especially those one coming from the exterior of a non-negative scale curvature. So what's definition? So in our results here, we don't really need to assume you have a feeling, but originally what Bartnik proposed is if you have a manifold with boundary, we still denote this by the interior matrix, and require the scalar curvature of this to be non-negative, right? And then he wants to define the quasi-local mass of this manifold with boundary. So then we propose, because I think it's done in 1989, and there must be a very exciting period of time where the positive mass theorem was just Riemannian case was completely solved in 3 dimensions, and there's so much progress breakthrough at that time. So he defined that to be extension, the ADN mass of the extension matrix. So this NGs will be so-called admissible. Right. So what would admissible? So the subtlety is really coming like a what compatible manifold you allow to compute the ADN mass. So first, if you are in the asymptotically flat setting, you want to be asymptotically flat, and the scale curvature non-negative. And then you want somehow the boundary data match. So you want to induce matrix on the boundary. So this will be the boundary. And now you look at the exterior. And then he used very different argument from why we call the boundary data, because he observed if you want the scale curvature to be distributionally non-negative across the boundary, then you need this assumption. So originally he proposed the induced mean curvature has to be equal, but then we know it just need to be one side, right? So I think is that right? Interior is larger than the outside. And then there'll be some no horizon condition. You want extension to have some geometric property. This is the most subtle condition. So there are actually different version of it. So for example, there's a one I think originally proposed is no closed minimal hypersurface inside. Right, and then this is a definition which I think mathematicians use more often to define some quantity. And now the question will be, when he proposed the definition, he will say whether, for example, whether there is a admissible family, right? So let's relate it to the scalar curvature extension result, which has been tremendous progress by Bartnik, Zhongshan An, and many recent work. And then he asks, okay, there is some, at least the set is not empty. Now you start doing infima and whether the minimizer exists. So he proposed a series conjecture, mass minimizer. And if it exists, is that unique? And then if it exists, what property does it have? So in view of the positive mass theorem and also the parallel inequality, the minimizer always has a property being static manifold. So he proposed this minimizer must be static vacuum. And this is in fact proved by Covino in this scale curvature deformation result. And also the further improved by using different method by Bartnik and Anderson-Gergi. Variational argument really use the variation of the rigiditable functional we seen earlier. Right. So this, the current status, I think, to my knowledge, is the counterexamples we mentioned for the one-side embedded surface is a counterexample to a case where mass minimizer it does not exist. Right, so that particular one. With the induced Bartnik boundary data from Euclidean matrix, and then if you want to consider this omega, with in fact with Euclidean matrix, I think the minimizer must be Euclidean, but then we mentioned the Euclidean matrix is not a valid thing because the injectivity boundary from outside is 0. So then they say the mass minimizer does not exist for that case. So I think it's still very interesting to my knowledge is to find out under what condition a mass minimizer exists. So like a affirmative statement. To my knowledge is very open. The metric, right? So the metric will be so I think matrix outside you can assume smooth, right? So when you except when you glue the matrix inside, it will be Lipschitz. But I think there is some results to show if it's a mass minimizer, then it actually be more regular, probably C2 alpha, if it's a mass minimizer.
So this is like a follow-up.
Follow-up.
Saying it's a mass minimizer static vacuum and it's two.
Oh, the exterior. Yeah, sorry, exterior. Max minimizer, I'm sorry, referring to the exterior region. So this is the exterior. Yeah, so it's a bit confusing from my notation. So this in my notation, we should be M, remove omega, right? But in this setting, we don't really know omega sitting inside M. So M is outside. So this is exterior. So outside, we don't really know what happened inside, but outside has to be, static vacuum. Right. But I think even it's smooth, it doesn't mean it has to be static vacuum all the way there. of course, you can have smooth manifold like the Euclidean. You can just perturb it. Of course, you cannot do that.
But I mean, the condition that MG is admissible is that it satisfies everything you said, plus G is smooth and Lipschitz across the boundary. Or is it different than that?
Right, so you don't define across the boundary, it's only interior, right? But the thing, the boundary has this condition. But then you can probably, so the thing is that this is you have to formulate when you study this problem. Everyone formulate differently, right? So what would be the regularity you needed in order for your argument to work? But usually they don't assume what the matrix across it, because this only, you should think about inside is fixed. But now you are just have the boundary, have the matrix defined up to boundary. And then you want to say up to boundary, what kind of property you get.
Yeah, but if I can like have a corner, and have a really bad corner, then it's going to change everything.
A bad corner. So
if the derivative of the metric is like really bad.
right, so you will assume not very bad, up to boundary.
Sure. But,
Yeah, so for example, like a C, you can even assume C infinity is up to boundary, but I don't think, so I think C2 or alpha is most regular, most reasonable assumption, right? If you are not looking at like a rough solution, but then even if you assume this, I don't think it will simplify the problem greatly. So the analytic setting is really depend on how your argument will make it work.
But the
up to boundary.
The outcome of the outcome of these conjectures, naively, like from my naive perspective, the outcome of this thing will depend massively on like how bad the formula is allowed to be.
So in fact, it will heavily depend on how you formulate your admissible family.
Right.
There are tons of literature, and almost everyone formulates slightly differently, right?
I mean, if you're asking a question of existence,
Yeah,
right, then the less regularity you ask for,
definitely.
the more likely you're to get it. And if you ask about the properties of the minimizer, the more regularity you ask for, the more properties you're going to be able to get, right?
Yeah, that's a
So-
good comment. Yeah.
Yes. So I'll just say that the standard thing is you would expect not much better than what's on the board. So if it's just the tangential parts of the metric matching, then basically Lipschitz.
Sure, but but this is what I'm saying. Like if you that's why I was saying if you have Lipschitz, then the existence, you have a better chance of proving existence than if you drop them.
Right. So for that, then you will probably have a regularity theorem to show once you have existence in a weak function space, then you're actually more regular than you think, right? So there will be something, right?
And just to clarify, the work that you're mentioning here, Bovino, Bartnik, etc., that's just for the exterior, so they don't say anything about what happens across this boundary.
Right. In fact, you don't expect, because omega and GI is fixed, right? So you don't expect you will change the property of it. Okay. Right. So so of course this is already quite open questions for a long time, and I think interesting for some quite many people. And there's also, if you are still not happy with this list, then you have all the general initial data sets you can work on. So this also defined for the general initial data set. So every question here has an initial data set version, which I will not go into detail, and much less has been really studied up, because the question is the setting seems quite complicated, right? Because you have really just the constraint equation to work on. But recently there's a progress toward the third part, right? So so the third part will be the mass minimizer, which will be initial data set. Mass minimizer is stationary vacuum. Or not. Right, so there's work by Covino. So basically he trying to extend this thing, but then this work shows you is some, you get kernel element of the static vacuum operator, right? And Covino work show this one is the kernel element of some operator, but which really have no significant physical meaning. It does not seem to correspond to stationary vacuum. Zhongshan An. So she proved for assuming 3 dimension, and if it's vacuum already, and then she proved it's stationary. And in my work with Dan Lee, we get I think we give a more complete answer analogous to this combination. So we show it's a kernel of some analytic operator, but then it turns out we show that it actually corresponds to a space-time. So it will be the mass minimizer has to be in a no dust space-time. But also surprisingly, we found out the conjecture will be false in general dimension because the space-time doesn't need to be vacuum. And we have an example coming from so-called the PP waves. And this is the one I'm going to speak at the conference. Okay. Yes.
Again, same question, but different.
Please.
So you said that the mass minimizer is static vacuum, just say the Riemannian case. You said actually what those theorems show, what it works is that you actually get regularity as well for the exterior measure.
Sorry, it's not really say that. So this assumes some suitable regularity. It assumes mass minimizer is like a C2 alpha, and then it's static vacuum. Of course, it's static vacuum and it's analytic. You can say that way, but it's whether I think it's more like this part. If the mass minimizer exists, then you actually know. Correct me if I'm wrong. So I think you can actually show the mass minimizer must have equality. You cannot have strict equality, and so you must have equality. So you have some further property to show if it's mass minimizer and what stronger property along the boundary you can show.
So then the initial data set positive mass theorem with corners would generalize that to initial data sets. Is that right? So like theta plus is equal to theta plus.
I will expect that, but it's not been proven yet.
And also just to understand, so in all these works, you just like so for instance in Covino or in An's work, you assume, you said she proved it if you assume that it's vacuum ready.
Yes.
Then she proves it's stationary.
That's right. So the proof, so assurance is vacuum, and there's a Killing vector field, which is time-like at infinity.
Okay. Then she proves that it's actually stationary. But does she get? So what regularity does she get? Then does it have to be?
So I think in this case, you will probably always assume it's like at least something, either C2 alpha or like a W2P to begin with, and whether stationary is analytic, stationary vacuum is analytic is a separate classical result.
Got it.
Okay. And I think so this really is the motivation of, to my knowledge, why when people will expect the static vacuum extension conjecture, right? If all those theorems, if all those conjectures are proven true, then you must have a mass minimizer. And then the minimizer must be static vacuum. So you must have an extension, static vacuum extension. And then it must be unique. So it will be our static vacuum extension conjecture will be consequences if all those three are correct. But then we know in general it will not be correct. There's some counterexample to this one. And then it turns out it's a totally different set of approach for the static vacuum extension conjecture, which I present in this mini course. I think to put this existence result of the results we have in more close contact with this quasi-local mass business will be possibly the following. I think it should be interest, and I really indeed must be correct on the sound assumption. Yes.
So really, uniqueness just follows once you have existence.
Oh, we no.
So if it exists, and then it's an analytic by static vacuum, so there's a uniqueness.
Right. The problem is the analytic, they only coincide at some degree on the boundary. They don't coincide in open sets. Right? Then it does not imply it has to be.
And in your counterexample with Dan, does that mean that the class of counterexamples you produce, does it have anything to say about uniqueness? Because you say it's not stationary vacuum. So does that mean you can get like lots of minimizers? It's not unique at all.
So its counterexample is that we can find some region, initial data set with boundary, such as the extension will have zero mass, but non-zero EMP. So it will not be and will not be vacuum, will not be Minkowski. But we don't know if for this boundary, that particular boundary data, whether there will be another extension, which we don't know.
I see. There's no like freedom in your class of counterexamples. It's just the counterexample.
It's just a counterexample, right? It's not like constructing. So we actually have an explicit example of asymptotically flat initial data set with certain property. And then for that, so it's actually quite large family. There's some matrix we can, like a matrix and second mononomial we can change. It's actually in a large family, but it's always fixed on initial data set, complete initial data set. We said there is some compact region inside this initial data set, which will be counterexample to the stationary vacuum conjecture.
And it's a contradiction to the vacuum part, not the stationary part.
Also, conjecture is kind of mixed. People believe stationary in some definition will be has time-like Killing vector field at infinity, right? And in that case, it's also very special case. We show the Killing vector field must be null, will not be time-like. So it contradicts both things. All right. So I think it will be related to compactness. This will be a general theory is like a compactness of rigid flat matrix, right? So here I'm just asking about compactness of static vacuum matrix. So I think the setup will be, again, we have omega. We can even work with, probably let me not fix omega, but here we have boundary, you have an exterior here, and then you have family of static vacuum. Matrix, and now N is the exterior. You have family of it. Suppose you know the induced Bartnik boundary data converge in some good space you like a C2 alpha or something, converge to some tau and phi. Whether the this sequence has convergent subsequence. I want the convergent subsequence to be in the weighted Holder space. Then we can control, we know the mass of the limit of the limiting metric related to the sequence. So this is a space where we know the mass is continuous. So I want to say whether you can find it. I think the only, again, correct me if I'm wrong, the only result I see regarding this is the work of Anderson Curry. In the same paper, I've been quoted several times, is they put the assumption if sigma is outermost in all those sequence. Because there's a problem, there's an issue if you have an injectivity radius goes to 0, and then they use this property to show the injectivity radius has from the boundary has a uniform lower bound. And I think it's quite hard to extract what exactly they prove in that that part, but I think they prove there's a subsequent convergence to some static vacuum matrix. Subsequential convergence. But it's not clear is what the space it converged to, because you can use the exhaustion method. You use the one you cut off at like big ball, right? And then you have on the big ball, then you have the theorem for the rigid flat. You can apply then this is really related to the space-time rigid flat, and then you have convergence there, and you just do the exhaustion sequence argument to show it does converge to some static vacuum matrix. But the question is, it's not clear in what space, what function space this thing will be.
What is outermost?
Outermost will mean it's outermost in with this G, I, it's outermost in.
Outermost what?
It's outermost means area outermost.
Oh, area outward.
Yeah, sorry about that. Area, thank you.